Hello, my name is Steven, and today I'm going to talk about my predictive modeling pipeline for the Home Credit Default Risk Hackathon. Predicting loan defaults is one of the highest stakes problems in machine learning because the cost of errors is asymmetric. A false negative exposes the bank to a lot of financial risk, while a false positive unfairly denies a person access to capital that they might deserve. Therefore, the entire pipeline was engineered around responsible AI, focusing on rigorous validation, fairness, and actionable explainability. Before training, I had to address the large amount of missing data in the property and buildings data. Instead of blindly adding columns that were missing over half their data, I dropped them to prevent socioeconomic imputation bias. So we ensured that we did not penalize applicants simply because they rent or live in areas without formalized building registries. Additionally, because explainability must be actionable, I translated machine variables into human variables. I converted days birth into age and years and engineered a credit to income ratio so our final XAI charts actually make sense to a loan officer. To ensure the model's performance wasn't arbitrary, I established a logistic regression baseline and compared it against a light GBM classifier. I utilized randomized search CV to rigorously tune light GBM's hyperparameters through cross-validation, applying a dynamic class weight to force the algorithm to prioritize the rare 8% of defaulters. For validation, I use a strict 80-20 stratified holdout set because 92% of the data set is negative. Standard accuracy would be misleading. I evaluated the model using ROC AUC, but more importantly, I relied on PR AUC, average precision, to provide a much harsher and realistic view of how well we catch the minority default class. To understand how the model behaves at a portfolio level, I generated a SHAP summary plot. It clearly identified that external credit ratings and the applicant's credit to income ratio are the biggest systemic drivers of default. I also generated partial dependence plots with embedded ICE lines. While the PDP shows the average global trend, proving that risk spikes as the debt ratio climbs, the ICE lines track individual applicant trajectories, ensuring that this global rule holds true across different applicant subgroups without any hidden variance. While global metrics are great for executives, underwriters need specific instance-level explanations. I implemented Lime to visually break down exactly which features push a specific applicant over the rejection threshold. I took it a step further by also generating counterfactuals. If a loan is denied, the applicant would be able to know why and what they need to do to fix it. My counterfactual analysis algorithmically alters the rejected applicant's data to find the exact approval threshold. For example, it could tell a loan officer if this applicant reduced their requested credit amount by 30%, their probability of default drops into the safer zone, and then they could be approved. One of the main requirements of the hackathon was ensuring that the model doesn't discriminate, so I built a custom fairness audit to test for equalized odds across two protected classes, gender and age. Unlike simple parity, equalized odds checks both the false positive rate, falsely denied loans, and the true positive rate across groups. I made sure that the variance between men and women, as well as applicants over 50 versus under 50, remained balanced. This proves that the model is making equitable decisions based on financial behavior, not some sort of demographic bias. Finally, I saved the fully trained model and data cleaning steps into a single file and used it to successfully score our holdout test data. However, ethical deployment requires acknowledging limitations. Our dataset lacks granular geographic and racial demographic data, meaning hidden proxies could exist. Furthermore, the model is vulnerable to data drift. For example, if there was a recession, income distributions would shift. Therefore, this pipeline requires a continuous drift monitoring and a human-in-the-loop fallback, ensuring borderline algorithmic rejections are always reviewed by a human who can always understand the real-world context. Thank you.